I meet Wojciech Zurek, a leading authority on quantum theory. Originally from Poland, now at Los Alamos, Wojciech explores the deep meaning of the quantum. I hear he's a character.
The reason we need to understand quantum theory before we understand reality is that quantum theory is the only theory which is encompassing everything. It has no limits. Quantum theory is weird. It is weird because it's so egalitarian. In quantum theory, any superposition of states is a legal state. Now, I know it sounds mysterious.
Tell me what that means.
This means that if this glass can be here and it can be there,
Yes.
it can be also in here and there at the same time. We don't see things which are here and there. We see things which are localized, which are in definite places.
And we see that no matter how small we look at things. In microscopes, we never see things in two places.
In microscopes, you have evidence of things being in two places, right? So in some sense, for example, electron microscopy works because things are in many places at the same time and then get recombined, okay? So microscopy, electron microscopy, is there because quantum mechanics is there. In fact, you know, if you look at applications, a lot of that is because of quantum mechanics.
Yeah.
Transistors, computers run because of quantum mechanics.
Let's understand the weirdness. The weirdness is this superposition.
The place where the weirdness starts is a superposition.
And it gets weirder.
It gets weirder.
Tell me.
The weirder part has to do with the fact that in classical physics, if you have a well-defined state of an object which consists of several pieces,
Yes.
this means that you have a well-defined state of each of the pieces. In quantum mechanics, this is not the case. In quantum mechanics, you can know everything that is to be known about a collection of objects, and yet you can be left in a situation where you know nothing about any of the parts. So these are the entangled states. So entanglement is an intimate knowledge of two particles about each other. And that knowledge is so intimate that it precludes any communication with anything else. So these two particles know about each other so well that indeed if you ask a question of one of them and it gives you the answer, the other one will give you a correlated answer.
No matter how far away.
No matter how far away. So the interaction doesn't matter. The state is a shared property.
And the particles can be so far apart that even light would not have a chance to communicate between
And
them.
this has been confirmed experimentally.
I'm more mystified now. How do we make progress in understanding this? Is it possible?
It is possible, and I think one of the links we were missing until recently had to do with our prejudices of how we understood classical theories. In classical physics, we always thought that a system by itself is something to be understood really in separation from the rest of the universe.
Okay.
Now, in quantum mechanics, it turns out that because of entanglement, the nature of these interactions, the consequences of the interactions are so subtle that the fact that even very weak interactions exist can change the behavior of the system in a very dramatic ways.
Oh.
So in fact, the most quantum aspect of quantum mechanics, which is entanglement, can help one understand how quantum mechanics ends up explaining what we see, classical.
So, help me understand how superposition, how entanglement can help us understand how the micro world explains the macro world.
The key point is that quantum systems are not isolated. They interact with the environment. When they interact with the environment, they leave records, they leave memory in their environments. So there is a transfer of information. So the interaction with the environment allows the environment to know where an object of interest is.
And before that, it was just a probability of where it may be.
It's worse than that. So before the interaction with the environment happened, you had oodles of possibilities, essentially all of them incompatible with what we see in the real world. after that interaction happens, you end up being offered a menu, but that menu has only on it positions which are classical, quote unquote. It doesn't tell you which one of them happens, but it tells you the set of possibilities. And the set in models that we can calculate is classical.
And that's the probability.
And then you can say, I assign probability to this set of possibilities.
Okay. So how then can we go back and say, well, what is really happening in quantum theory? Is this just a mathematical formulation that is a kind of a way to understand some reality, or is this really what's happening?
Now, we know that components which make objects which we deal with are definitely quantum. So the questions that can arise is, does anything strange happen when these objects get bigger and bigger?
Right.
Nothing seems to. Everything seems to be still quantum. So if you're in a controlled situation, when the system is isolated, it behaves as if quantum laws were sacrosanct.
The isolation of the
no
environment
choice.
is the key. It's
So
not
the-
just the size, because
Absolutely.
the size can get bigger and this quantum weirdness is maintained.
So you put your finger on the key thing. If the system gets bigger, it's harder to isolate from the environment.
yeah.
So if something is as small as an atom or an electron,
It's easy.
well, you can make it separate and keep it carefully away from everything else. But if something is as big as a glass or as you or me, that's impossible.
Let's drink to quantum mechanics.
Let's drink to quantum
I
mechanics.
understand it a little bit better.
Let's drink to it.